Hello, my name is Will Paris, and this is my Lab 5 Magnetic Braking with Faraday. So this lab was conducted in order to observe the behavior of a magnet falling through an aluminum tube in order to visualize Faraday's law. In order to perform these procedures and calculations, we need a strong grasp of many physics fundamentals, such as Faraday's law, Biot-Savart law, Newton's second and third laws, Ohm's law, and the time derivative of magnetic flux. In this lab, we found that the experimental time for the drop is 1.8 seconds, and the true time, and the model time would be 1.705 seconds. We're assuming in this lab that air resistance is negligible, and gravity and magnetic force are the only two forces acting on the magnet. So first we must describe our systems and our surroundings. Our surroundings are the aluminum tube and the magnet. The system are the aluminum tube and the magnet, and the surroundings are everything else. So the procedures of this lab were to find the magnetic north of the magnet with a compass, and then just to drop the magnet through the tube 5 times and record the time that it took to fall through each time. So this is the data we collected about the tube and the times. The length of the tube was 0.45 meters, the width 0.006 meters, inner radius 0.024 meters, radius 0.03 meters. The mass was 0.025 kilograms, and the average time was 1.8 seconds. And then, as you can see in our table to the right, all of our 5 trials were listed with their times. So this is my code that I used to create the model of the magnet falling through the tube. So as a result, we can see that the model shows us the velocity with respect to time of the magnet falling through the tube on this graph to the right, and it also gives us the time it takes to get through the entire tube. Lastly, we have a visual of the tube, and as you run the function, the red and blue rings fall through the tube like the magnet does, and it shows us the direction of the current flowing. The error between the experimental time and the model time is probably due to human error. It also could be due to an incorrect mu for the magnet, as we use the mu we found in lab 3. So what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? So if the resistivity of the conductor were reduced as close as possible to 0, according to Ohm's law, the induced current would be much greater in the tube, and that would create a much greater magnetic force, slowing the magnet down more. And then what if holes or slots were cut into the tube? How would this affect the ring currents in your model? Well, this would in fact also be similar to Ohm's law. The induced current would be much smaller. This would create much less magnetic force, and this would allow the magnet to fall more freely, or less time in the tube. And then this, I think, is all for my Lab 5 magnetic braking with Faraday.